Hey everybody, Mr. Mac here. In this video, I'm going to do some of the solutions for 1.3 radicals and rational exponents. You have the solutions for the odd ones, so I think I might just focus more on selected even problems. So for the following exercises, simplify each expression. Okay, so we have the square root of 256. Well, 256 is a perfect square, and we could make a factor tree for this, but it's kind of one of the ones that maybe you might want to memorize, and the square root of 256 is 16. So we've got the square root. So I took care of the square root on the inside here is 16, and then now the square root of 16 is 4. And so that's my final answer right there. All right, let's take a look. Let's do number 8. We have the square root of 289 minus the square root of 121. These are also perfect squares. You can put these in your calculator, square root of 289, and check it and see if it works out to be an integer. And if not, then make the factor tree. So the square root of 289 is 17. And the square root of 121 is 11. And 17 minus 11 is 6. All right. Number 10 doesn't get any easier. Another perfect square. Square root of 1 is 1. Easy enough, right? Okay, let's take a look at number 12. So the square root of 27 is not a perfect square. If we were to make a factor tree, we know it's not an even number, so 2 doesn't go into it, but 3 does. So 3 and 9. And then 9 can be factored to 3 and 3. Notice I want to put my prime factors on the left until I've done them all. And now I circle my pairs, and I have an odd 3. So another way, if I had to write this another way, I could say this is 3 squared times 3, right? And when I take the square root of 3 squared, the 3 comes out, right? Because 9, the square root of 9 is 3, all right? So this is what I'm thinking here. I'm going to back up. So 3 comes out, and this 3 right here still has to stay in. And the square root of 64, 64 is a perfect square, so that would be 8. And 3 and 8 doesn't simplify, so this is our final answer for this one. Okay, 12 is done. Let's see, 14. Square root of 800. Okay, so 800 is not a perfect square. Whenever we see a number that's in the hundreds like this, 800, 900, 300, it always has a factor of 100. So take a look at this. We could rewrite 800 as 100 times 8, right? And what do we know about 100? It's a perfect square, isn't it? Square root of 100 is 10. So this 10 we could bring out. And the 8 was right here. Well, there's a perfect square factor in 8. If I make a factor tree here, we have 2 and 4, and then 2 and 2. So I have a pair of 2's here, and an odd 2. So I'm going to take that one pair of 2's out, and the odd 2 stays in, and 10 times 2 is 20. Now we could have done the factor tree on 800. And it's a big factor tree. It's going to be a little long, which is fine. But I want you to see, if you know that there's a perfect square factor like 100, then go ahead and take that out and start making your life a little easier. Okay. 16, this one is going to have an extra step here that we're going to do. So the square root of 8, we just did the factor tree for 8. So we know a 2 is going to come out. Okay, so, before I did that, I'm going to leave it there, but I want to show you, we can rewrite this as the square root of 8 over the square root of 50. Because then that might help us break up this problem a little bit more. And we're using the quotient rule here. I'm looking at my notes to see what example it was. It's from example 4. So breaking up this fraction under one big radical into 2 separate ones. And so I also have this 50 right here. So let's make a little factor tree for 50 and see if anything comes out. So I know 50 is 2 and 25. And 25 is a perfect square. Okay, so next step. I'm going to take, let's circle my pairs here. I have an odd 2. So my numerator, 2 comes out. Square root, this 2 stays in. Denominator, 5 comes out. And this square root of 2 stays in. And take a look at this. We have a radical 2 divided by radical 2. That's going to cancel out. And our final solution is going to be 2/5. And that's our answer. Okay, let's see. 18. Okay, well, I'll do 18. 18 is good practice for our bigger factor tree. So 192, we can test it on a calculator. Take the square root of 92. It is not a perfect square. You will get an irrational number. So let's take 192. And we know it ends in an even number, so it's divisible by 2. So 2 goes into 192 96 times. 96 is also even, so I'm going to take another 2 out. It's 48. Also even. 24, also even. 12, still even. 6, still even. 3, and we're done. I'm going to circle my pairs. So a pair of 2's there, and there, and there. Have an odd 3. So that means that 2 comes out, this 2 comes out, this 2 comes out, and the odd 3 has no pair, so it stays in. 2 times 2 times 2 is 8 root 3. Okay. That's how you do the factor tree. 20. All right, so we're still trying to simplify here. If we can combine these two terms into one, that would be ideal. So far, these two terms don't have a common radical here. The radicand's 5 and 45. We want to see if we can do something to make them the same radical so that we can add them. So we can't simplify root 5 any farther, but 45 is divisible by 5. It ends in 0 and 5. That means it's divisible by 5. And this is 9. And 9 is factored into 3 and 3. I have a pair of 3's. I have an odd 5. So this is going to be 15 root 5 plus 7. Now this 3 comes out, so this is times. Remember, guys, these are factors. We're not going to add 7 plus 3. It's all being multiplied here. 7 times 3, root 5. 15 root 5 plus 21 root. I wrote a 2 there. Let me fix that. Just going to back up here. 5 plus 21 root 5. Okay, so 15 plus 21 is 36. Root 5. And that is the solution. That's a simplified. Okay. That was number 20. So I can break this up into root 96 over root 100. Ooh, square root of 100. That's a perfect square. We can make a factor tree, but we shouldn't have to. You should recognize that. 96 might have to do a factor tree. 2, 48, 2, 24, 2, 12, 2, 6, 2, 3. Okay, I got some odd factors here that don't pair up. So two 2's come out, so that means I got 4, and a 2 and a 2 inside gives me 6. Remember, that's multiply. And I've got 10 on the denominator. Square root of 100 is 10. 4/10 simplifies, so I can take a 2 out. So it's going to be 2 root 6 over 5. Okay, let's see here. I guess I'll do 24. Well, I hadn't planned on doing all the evens, but it looks like I am. Okay, so the radicals are not the same. We cannot combine these, but the 75 has some perfect square factors in there. 75 is divisible by 5. 5 times 15 is 75, and 15 is 5 and 3. And I have a pair of 5s and an odd 3. So 12 root 3 minus 4. Now one of these 5s comes out, so that's times 5, and the 3 stays under the radical. 12 root 3 minus 20 root 3. And 12 root 3 minus 20 root 3 is negative 8 root 3. Okay, radical 405 over radical 324. So 405 ends in a 5, so we can take a 5 out. 5 goes into 48. 5's 81. Oh, look at this, 81. 81's a perfect square. So we can continue to factor this, but look at this, guys. I'm going to rewrite this right here. I'm going to say 81 times 5 over, okay, I know 81 is going to come out, so I'm going to leave it like that. 324 is an even number, so 2 goes in. So 2 goes into 32, 16, so that's going to be 162. 2 just is 81. Oh, look at this, 81. So I have an 81 again, and I also have a pair here of 2's. So this, I can rewrite this as 81 times 4. Well, guess what? 324 is a perfect square. If you put that in your calculator, you'll get an integer. You'll get a whole number. So let's see, what could we do now? How about let's take the 81 out here. So that would be 9 root 5. And the denominator, I would have 9 times 2. And then the 9's cancel. And my final answer is root 5 divided by 2. That's a 5. Okay. We're getting into some more challenging. Let's say challenging. Just we understand what we're doing. It's not hard, but there's some more steps happening here. We have 1 plus radical 3 in the denominator. So radical in the denominator is not considered simplified. So we need to get this out of the denominator. And the way we do that is by multiplying by the conjugate pair here of this binomial, 1 plus root 3, by this term. It's a term that has 2 parts to it, 2 terms. So we're going to have to multiply this by something that cancels the root 3. Now we know root 3 times root 3 gives us root 9, which is 3. So if I multiply this by root 3, it'll get rid of this part, but it'll just put it, when I distribute it, it just puts it to the 1. So the way we get around this is we multiply by its conjugate pair. So 1 minus root 3. And what we do on the bottom, we have to do on the top. Okay, so I'm going to distribute here. I'm going to wrap all these in parentheses here. So 5 distributed to the 1, and then the negative 3 gives us 5 minus 5 root 3. I'm going to do the whole thing on the bottom so you see it. Once you understand the pattern, you don't have to write the middle parts, but I'm going to show you that they cancel. So we're going to have to now FOIL, because we have multiplying 2 binomials. So let's do the first. 1 times 1 is 1. Let's go outside. 1 times negative root 3 is negative root 3. Now we're going to do the inside. Root 3 times 1 is positive root 3. And root 3 times negative root 3 is negative root 9. Okay, now look at this. 5 minus 5 root 3. That's still my numerator. I haven't done anything there. Look what happens with the middle terms. Do you see how they cancel? Negative root 3 plus root 3. And root 9 is 3. So the denominator ends up being just 1 minus 3. So I get 5 minus 5 root 3 over negative 2. Now we don't like to have a negative in the denominator, so I'm just going to multiply negative 1 top and bottom. And my final answer is going to be negative 5 plus 5 root 3 over 2. Box that in. Okay. Okay, so 30, we have the 4th root here. So this is, another word of saying this is what number, let's get what number here raised to the 4th power equals 16. Right, so the cube root of 16 is this number. The other way to think about it is I take a number and raise it to the 4th power, and that's 16. If I just write this as x, it would be something like this. X times x times x times x equals 16. what does this number have to be? I hope you see it's 2. 2 times 2 times 2 times 2 is 16. So the fourth root of 16 is 2. And the way that you really do that is just by knowing your multiplication tables a bit and just how you expand that to different roots. Okay? For the following exercise, simplify each expression. Okay, so we're trying to simplify here. So we have the square root of 4y squared. We're looking for perfect square factors. So 4 is a perfect square, so that can come out, and y squared is a perfect square. So simply, for this one, it's just 2y. Okay. Okay, and this one we're raising to the 1/2 power. So this is a radical in terms of an exponent. The way we could rewrite this if we wanted is we could say, let me get my colors right here, square root of 144 p squared q to the 6. You could rewrite it, but you really should get used to seeing this and understanding what it means. It's actually easier to use the exponential form of radical than writing the radical over the entire term in the long run. I'm going to do this just so you see that these two mean the same thing. 144 is a perfect square. Square root of 144 is 12. The square root of p squared is p. And the square root of q to the 6th is q to the 3rd. There's another way to think about this, and let me show you. So here's our solution right here, and maybe I'll just box that in. But I want to show you something else. I want to show you why, in some ways, this is easier. So if I go back to this form here, and maybe I'll just rewrite it. Do you remember what we did with our rules for exponents when we raising something to another power? We use the power rule, and in the power rule we multiplied. If you recall, if I had a to the m raised to the n, it was equal to a to the m times n. Okay, that was our power rule. So we're going to take this 1/2 right here and multiply it through our other exponents. So on the 144, remember there's a 1 here. So this would be 144 to the 1/2. Okay, so this one, 2 times 1/2 is 1. And 6 times 1/2 is 3. So this would be q to the 3rd. Now this right here still means square root. So we take the square root of 144 and it's 12. So we get 12p q to the 3rd. You guys see we got the same thing. Okay. Okay, so the square root here, let's simplify here. 3, nothing's going to happen with the 3. The m, however, right here, I could take out. So this would be 9m root 3. The 27 here is, remember 27 is 3 times 9, and then 9 is 3 times 3. A pair of 3's comes out, and there's an odd 3. So this would be plus 3 root 3. And I guess, so for this one, we really can't add these together because the m, and so we're just going to leave it like that. We could write it in another form, but we're going to leave it like this. It's fine. And 42. Okay, square root of 2n, nothing can come out here. I'm just going to rewrite that in the numerator. Now 16 is a perfect square. 4 comes out. N to the 4th is a perfect square. N squared. And then look, I have 4 both in the numerator and the denominator. That cancels out. So I get the square root of 2n over n squared. And I think I'll keep going here maybe. So what's next? $42, $45, $50's next. Okay. I think I'll do this last one here and make another video. Okay, square root of 20. I see some perfect squares in the denominator. 20, goodness. 20, it's still wrong color. No, that's right. This brush seems, I guess it's fine. 2 and 10. 2 and 5. I have a pair of 2's and an odd 5. So this is going to be 2 root 5. And then the square root of 121 is 11. The square root of d to the 4th is d to the 2nd. And it doesn't look like anything's going to simplify there. We look pretty good. Okay, I think I'm going to stop right there, and I'll do some more evens on another video. All right, hope that makes sense, guys. Check you later.